In Chapter 10, we're going to talk about how to use Monte Carlo simulations to price options. In the previous chapters, we have seen that we can derive the Black-Scholes formula, and the Black-Scholes formula gives us a closed-form solution to find the price of a European call or put option, but the Black-Scholes formula came with assumptions such as constant volatility through time and returns being normally distributed. We then saw that if you work with implied volatilities and construct a volatility surface, then you could actually work around that problem, that volatility has to be constant. However, one of the issues then is you need first a bunch of option prices which are traded in the market to figure out what are the implied volatilities and construct a volatility surface before you can price any new options. Another approach which we could think of is if you derive the Black-Scholes formula from a continuous time setting instead of as a continuous time limit from a binomial tree, then you can actually also solve the Black-Scholes formula in form of a partial differential equation, and that could also be numerically approximated, and the solution for option prices could be derived from there. Another approach which we have talked about is the binomial tree. The thing with the binomial tree was that although we can make it more general than the Black-Scholes formula, so we could allow for state dependence of volatility and interest rate, and therefore it can be a little bit more versatile. But one of the problems is that setting up the tree, you need really a lot of time steps for this approximation to be good, and that might be a daunting task to do. The approach which we're going to talk about here is Monte Carlo simulations, and the basic idea of the Monte Carlo simulation is that we approximate the expectation in the fundamental theorem of asset pricing. So if you think about the fundamental theorem of asset pricing, then we know that the price today of any risky security is going to be its future value at some maturity date capital T discounted by the risk-free rate and taking the expectation under the risk-neutral or this Q probability measure. Now notice that here I write that quite general, so interest rates may change through time, and so instead of just having interest rate R times the time horizon, I actually sum up all the interest rates between time small t and capital T, so allowing for interest rates to actually have different values at different points in time. Now what does this equation imply? It basically says that f follows a stochastic process where the value at time ti is equal to the value at time ti minus 1 plus then its previous value at time ti minus 1 multiplied by the interest rate at time ti minus 1 multiplied by the time horizon from ti minus 1 to ti, and then plus some volatility, which is a function of f itself, maybe some other state variables y and time, and that is multiplied by the CF thing, where the CF is a standard normally distributed variable with expectation 0, variance 1, and that's multiplied by the square root of that time interval between ti minus 1 and ti. F, you can think of it as any risky asset, but in particular here we want to think of it as an option. Notice that this y variable, this might be some kind of economic conditions. You could think of it as maybe aggregate GDP growth or whatever else macroeconomic indicator which you want to use, maybe unemployment and so forth. And this variable y itself is a stochastic process, so the value at time ti is equal to the value at time ti minus 1 plus some expected change mu y, which may depend on the current value of y and time, times the time interval between ti minus 1 and ti, plus this sigma y, that's the volatility of that variable y, which again may depend on the current state y and the time, then multiplied by the cy, where cy is also a normally distributed thing with expectation 0 and variance 1, and then multiplied by the square root of the time horizon between ti minus 1 and ti. And then finally, the interest rate, we also can allow that this is a stochastic process, so the value of the interest rate at ti is equal to the value of the interest rate at ti minus 1 plus some expected change in the interest rate, where this expected change might be a function of the current interest rate, these economic conditions y and time, times the time interval between ti minus 1 and ti, plus now the volatility of the interest rate, which again might be a function of the interest rate itself, the economic conditions and time, and multiplied by these shocks, C, R, and CR again is normally distributed with expectation 0 and variance 1, and then we have that multiplied by the square root of that time step between ti minus 1 and ti. These shocks to the variable f, to that asset price, to these economic conditions y and the interest rate, they may have some correlations determined by these raw variables. What is the problem? Well, we don't know yet what the function f is. That eventually we would like to know what that price is at time t, and we also don't know how these changes evolve of f, and in particular we don't know what that volatility is. So the interest rate we can actually observe, but what we do not know is how volatile is our price f. What we can do is we can estimate a price process for some underlying security. You can think of this, for example, as the S&P 500. And again, by the FDAP, we know that S takes basically the same form as F. And so we know that the price of S at time ti is equal to price of S at time ti minus 1, plus now it is expected to grow at the risk-free rate times the time horizon. And then it has some volatility, where again this volatility may depend on the current level of S and also economic conditions and time. And now you have some shock, where this is again random normally distributed variable with expectation 0 and variance 1 times that square root of that time step. Why is the expected return of S equal to the risk-free rate? That's because we are looking here at the risk-neutral probability measure, where every asset grows at risk-free rate. And that's in some sense, again, this model where all the asset prices satisfy this FTAP, where the return on each asset is exactly equal to the return on the risk-free asset. Now the trick is going to be we simulate S. So we start at the initial value of S, we draw random variable C, and we simulate the path for S. And to do that, of course, we also need to simulate R. So we need to draw random variables for R and potentially also for Y to simulate these paths for R and eventually S. And once we have potential realizations of S at the maturity, then we can say, well, the derivative which we try to price will be some function of that price of the underlying at that maturity date. So if you think about the call option, that function would be just the maximum between S at time capital T minus strike price or 0. If we look at the put option, then this function would be the maximum of strike price minus S at time capital T or 0. So depending on which option we want to price, we just use a different functional form. When we simulate data, we first have to approximate the time space between time small t, when we try to figure out what our option price is, and the maturity date capital T by n time steps. And so this n, how many time steps we have, will eventually determine how big one time step is. Well, it's just going to be the entire time length divided by number of time steps. That's going to be the length of one time step. Now, the approximation is going to be better if these time steps are as small as possible, but that of course comes at the cost. If you have more time steps, we have to randomly draw more variables C, and that just needs more computing power, and therefore our simulation will take more time to run on a computer. So what is the approach of a Monte Carlo simulation? If you want to simulate one possible path for our stock price, our interest rate and economic conditions, then we start at time t0 with a certain value of this asset S, the interest rate, what we observe today in the market, and our macroeconomic conditions Y. Next, we generate n random variables CTI. That's to model that stock price, the shocks by how much the stock price may go up or down randomly, and also n variables CR. These are the shocks which says whether interest rate randomly goes up or down. And then we also generate n random variables CY, which tell us by how much the macroeconomic conditions suddenly go up or down. Once we have generated these n random variables, we can plug them in these difference equations which you have seen before, and that will give us one simulated path for the stock S, the macroeconomic variables Y, and interest rate R. I denote by superscript J, that's for the simulated path J. Notice that this simulation is under the risk-neutral probability measure Q. Now, given this simulated path, all I have to do is I look at the final realization of S in that path J. Given that final value of S in that particular simulated path, I can now compute what is my option payoff in that simulated path. So that means now with these n random variables for C, CR, and CY, I was able to generate exactly one possible realizations of the underlying asset, and that then gave me one possible realization of the option. Now I can repeat that over and over again, and I can do that m times to simulate m different paths and therefore m different values of the underlying and that option at the maturity date. Once we have the m simulated values, then we can use the fundamental theorem of asset pricing, which says the price of an option is equal to its final payoff discounted by the risk-free rate and taking the expectation over this thing under the Q measure. Now I approximate this expectation by taking the average over the M simulated payoffs of the option. So remember, for each path which I simulate, I get one possible realization of the underlying asset, and that gives me one possible realization of that option in that path. And moreover, with that simulated path, I get one simulated path of interest rates, so I can now use this simulated path of interest rate to discount that possible realization of the option payoff at maturity. I can do that for all m paths, then I sum that up and divide by m, or in other words, take the average over all these realizations. That's an approximation for that expectation. In some sense, what you assume is that the probability of each realization is equally likely. Now, if you have many such simulations, so if m is very large, then this approximation of taking that average is going to be a pretty good approximation of the expectation. Now, of course, the downside of choosing m very large is that you have to simulate more paths, meaning simulate more of these random variables, which eventually is going to be time consuming because it needs a lot of computation power of the computer. So you're going to have to find a balance between how many simulations you want to do and how much accuracy you need for approximating this expectation, the FDAP, by taking this average over all these simulated paths. Now suppose that we assume that the Black-Scholes formula holds, so meaning that under the risk-neutral probability measure Q, the stock price grows by the risk-free rate, and that risk-free rate is constant, and also volatility is constant. Now in this case, it turns out that we can actually write the price of the underlying asset equal to the price at time small t times e to the power of risk-free rate minus 1/2 the variance of the underlying asset times the time horizon plus annual volatility times square root of the time horizon times some standard normally distributed variable c. This is nice because we do not have to simulate an entire path for these macroeconomic conditions y, an entire path for the interest rate, and an entire path for s. Why is that? Well, again, because interest rate is assumed constant, so well then there are no shocks to interest rate, so we don't need to simulate this thing. And the volatility over here is assumed to be constant, so we also don't care what happens to macroeconomic conditions. Now, we also don't need to simulate many of these values CT because we know that we can write this thing in just one go by simulating one random variable. And this is just a special case what you can do if R and sigma are constant. So then simulating one path is very easy. I just have to draw one random variable. Now the payoff of a European option, once I draw a random variable and have one possible realization of S, is then just again given by whatever option I would like to price. And again, now I can take the average over all these and discount them by the risk-free rate. Notice that now this discounting by the risk-free rate, I can move this out of that sum, and that's because, well, the interest rate didn't depend on that simulated path J. Going back over here I cannot do that because the simulated path for R will actually depend also on which simulated value I have here for S. Here doesn't matter because R is actually independent of which path I have, or the discounting is the same for each path. So we see that using our Monte Carlo simulation becomes quite simple under this Black-Scholes assumption of constant interest rate and constant volatility. Now we can also price path-dependent derivatives. These might be some exotic options, like for example Asian options or barrier options. And why can we do that? Well, it will be very simple for us to define the payoff of an option, not just depending on the final realization of the underlying, but depending on the entire lifetime of the underlying, whether it used to be very high at some point in time or very low. And similar, it can also depend on whatever realizations I had in the interest rate or some other macroeconomic variables. Since I have simulated these paths, well then whatever function I want to apply on that, I can get that payoff of the derivative. Once I have the payoff, again I discount that by the interest rate, take the average over all these discounted payoffs for each path, and that gives me an approximation for the expectation, and that's by the FDAP then the price of my derivative at time t. American style options are a little bit more difficult because for American style options you have to decide at which point in time is it optimal to exercise. And to do that in the binomial tree, what we had to do is work backwards in the tree and decide at each point in time, is it better to exercise early, yes or no? With a simulation approach, we actually don't know at each point in time what the value of our option is because we don't simulate the option price itself in each of these paths, but we only simulate the price of underlying asset, risk-free rate, and some macroeconomic conditions. So therefore it makes it kind of difficult to figure out whether exercising early is optimal or not at a certain path at a certain point in time. The way people deal with this problem of figuring out whether to exercise early or not is they basically define some functional form depending on the state variables to decide when you should exercise and when you should not exercise. Once you have the functional form, well then you can just basically make the payoff of the option depend on the entire path, because then you can decide whether the option is exercised early or not in a given path, and then you can proceed to figure out what is the discounted value today and take the average over that under the Q probability measure. However, the tricky part is how to find this functional form, and that you have to first calibrate. And that's something which we are not going to go into in this course, but I just want to mention that there are ways to do that. Once we have approximated the price of an option at time t using the average over all the discounted payoffs over all these different simulated paths, then we also want to figure out how accurate is our approximation. So how well do we actually do if you simulate m paths with approximating these expectation under the Q measure. To do that, we would like to figure out what is the standard deviation on our approximated value f. Well, standard deviation is square root of the variance of f. And what you do now is you just plug in for f this average over all the discounted payoffs under all these different m paths. And notice that each simulation is actually independent from all the other simulations. So the variance of the sum over these payoffs, which are discounted by the risk-free rate, is the same as the sum over the variance of all these things, where if you move 1 over m out of the variance, it becomes 1 over m squared. And notice that all these variances are the same, because for the simulation I have the same conditions. There's no difference between one or the other path in terms of simulation parameters. So well, the sum over all these variances is just m times the variance over one of these paths. So that m times cancels out with the divided by m squared, and so all I'm left with is divided by m. Now, how do I figure out what is the variance of one simulated path? Well, to do that, we just take all our m simulated paths and we see how much they deviate from the average value, where the average value is just our approximated price by the FDAP of the option. We look at how they deviate from the average, square that, divide by number of paths minus 1, which we have. That's an estimate for our variance. That variance of one simulated path, that should eventually converge to some finite number, and therefore as you increase m more and more, overall the standard deviation of our approximation is gonna decrease as m gets larger and larger, but it's only decreasing in the square root of m. So what does it mean? It means that if we increase m larger and larger, then the error or the standard deviation of our approximation becomes closer and closer to 0. But on the other side again, if we choose m very large, it is actually costly because it will take very long for our computer to simulate more and more possible paths, and therefore this will take a lot of time. The last thing I want to talk about is how to compute Greek letters in the Monte Carlo simulation, and then we're going to look at a specific example of a simulation. So for the Greek letters, remember the definition of, for example, delta is by how much does the price of the option change if the underlying price changes a little bit. And so the way you can approximate that in a Monte Carlo simulation is say, look, do one simulation where you start with an underlying price ST0, and then do another simulation where you change with a slightly different price ST0 prime, where ST0 prime is a little bit larger than ST0. So you can now get approximated option values using the approximation of the FDAP through these Monte Carlo simulations, both for this option price given that underlying price ST0, and then for the option price given the price ST0 prime. Now you take the difference between these option prices divided by the difference in the stock prices. That gives you this sensitivity of the option price to small changes in the underlying asset, and that's by definition delta. Now if you do these two simulations, of course each simulation comes with some approximation error, which again it was captured by the standard deviation of our approximated value. And so you have to be a little bit careful, because if you take different simulations across these two values, then the approximation error may also show up in your delta. So what can you do? One thing is for the randomly drawn variable, which help you to simulate f over here, choose the same randomly generated variables to approximate that option price f over here. That will allow you to reduce approximation errors in the delta. The last thing I want to do is look at a specific example. Let's look here at something which probably resembles reality quite well. We look at an environment where we have an asset price, which is again under the Q probability growing at the risk-free rate, and then it has some volatility, and that volatility can actually stochastically change through time. And in particular, we define the volatility as the square root of the variance V, and V itself is a stochastic process which has a volatility by itself, which is multiplied by this random normally distributed variable CV, and that CV is correlated with the standard normally distributed variable C, and V is actually mean reverting, where VL captures the long run mean of the variance, and MV over here tells you how fast variance mean reverts to its long run mean. So meaning that if you were today at the long run mean value, then in expectation you think the variance is not going to change, but now there might be some positive shock to it, which tells you, okay, tomorrow variance is higher. After that you expect it to mean revert towards the long run mean, and there might be new shocks coming in. So variance can then change randomly through time. Moreover, we assume also for the interest rate that the interest rate today depends on interest rate yesterday. There is some long run mean of the interest rate. There's some mean reversion, how fast it goes back to its long run mean. And then again, interest rate has some volatility. And then we have these shocks to the interest rate, which might be correlated to shocks to the stock price and also shocks to volatility. Now, if I choose a parameterization, I choose all these variables here, the initial price of the stock, the initial interest rate level, R bar, that's actually the same as RL here. That's the long run mean of the interest rate. I choose how fast it mean reverts. I choose the volatility of the interest rate. I choose the initial volatility, and sigma I denote here as the square root of VL. That's the long-term sigma to 15%. I choose then the mean reversion of the variance, and then I choose these volatility of the variance itself. And then I choose the correlations between the shocks of variance to interest rate and the correlations also to the stock price. And then these parameters phi r and phi v, they just kind of tell us how much we scale these volatilities, but we don't need to worry about this thing too much for now. What I want to do is now figure out what is the value of an at-the-money call and put option. So I set strike price equal to 100, which is same as the current price of the underlying asset. I want to look at a maturity of 3 months. I slice that up in 100 time steps, and I'm gonna simulate 10 million different paths from my simulation. So what does this mean? For each path which I simulate, I randomly draw 100 variables C, which are the shocks to the underlying stock price. I also draw 100 variables CR, which are the shocks to interest rate, and 100 variables CV, which are the shocks to volatility. So that gives me one path, which then gives me one value of the underlying asset at maturity. And then once I have that one underlying asset at maturity for this one path, I use this function to determine the call price at maturity. I use this function to determine the put price at maturity for that one path. Then I take this potential value for that path at maturity of the call option discounted by the risk-free rate, where again, that's just all the simulated values of the risk-free rate over these 100 time steps, and similar for the put. And then I do that 10 million times for 10 million paths, and I take the average over all these values. That gives me a call price of $2.8836 and a put price of $2.6330. If I compute the errors of this approximation, so using this formula over here, then again, how do I do that? For each path, I take the discounted call price and look at the difference to the actual call price. So for each path, I take basically this thing over here, look at how much this deviates from my average discounted value from this $2.8836. That's what this thing is. I square that, and then I sum up that for all the different paths, divide by m minus 1, take the square root of it, and divide by square root of 10 million. And that gives me the standard deviation for the call option approximation of 0.0009, which is quite small because it says that if I'm wrong by 2-3 standard deviations, it's basically still gonna keep my call price equal to about $2.88. So it seems like this approximation is pretty accurate because again it comes with very small errors. Similar for the put price, I can compute a standard error, and again this is pretty small. Even if you're like 3 standard deviations away from the truth, it's still gonna be basically accurate on 2 decimal points. You may ask now, well, yes, you gave me all these formulas, I know how to compute the standard errors of this approximation, and it looks like a small number that would indicate that our approximation here of these call and put prices are good. But is this really true? Is there any way to verify that this approximation is really good? And yes, there is one way to do that. Let's suppose we want to go back to a Black-Scholes setting, so where the interest rate is constant, and I can do that by setting the volatility of the interest rate, so this sigma r thing, equal to 0. And where also volatility is constant. So I set the volatility of the variance, this sigma v over here, this one equal to 0. And now I do exactly the same simulation again. So now if interest rate and volatility are constant, then we know actually that I'm in a Black-Scholes setting, and I can also use the Black-Scholes formula to compute call and put prices. If I use the Black-Scholes formula to compute the price of European call option, that gives me $3.1141. If I do my simulation, where again interest rate and volatility don't have any variation, so they're constant, then my simulation gives me also a call price of $3.1141. The volatility of that approximation is 0.0011, which is very small. Now you see actually I get exactly the same call price, whether I use the approximation using Monte Carlo simulation or the Black-Scholes formula, which now says indeed this approximation works really well. Similar for the put price, if I run my Monte Carlo simulation and use the approximation, I get $2.8644, and actually this is exactly the same again as the put price from the Black-Scholes formula. Now there might have been some deviation, so I guess I got a little bit lucky, because it could have been that the put price might be maybe 0.0009 points higher or lower, so it could have very well been 2.8655 or something like that. Now it turned out that it's exactly the same value. In any case, it illustrates that our simulation works actually pretty well if we use these 100 time steps and these 10 million simulation paths. Now going back one slide and looking at the call price of $2.8836 and compare that to this $3.1141, what's the difference between these prices? Well, that's because in the setting over here, this takes into account that interest rates are time varying and volatility of the underlying asset is changing through time. While here we assume they are constant. So you see that if you do not take into account this time variation in interest rates and in volatilities, then your call price might be quite a bit off, and it's actually almost 10% difference between these prices. Similar for the put price, if you take into account time variation in volatility and interest rates, then you get a put price of 2.633. And if you do not, then you get 2.8644. So again, this is almost a 10% difference. And again, if you would actually believe that in the real world interest rates and volatilities are changing through time, then using the Black-Scholes formula pretending they are not, so they are constant, that might be a quite big mistake because you get very wrong put and call prices. The last few pictures here, I'm just showing you one simulation path for the interest rate. Is again, we start at 1% interest rate, Then we randomly draw these CR variables, and the interest rate moves around. It may deviate from its long-term mean, which is 1%, but it's slowly getting pulled back. Then you have a series of shocks which drive up interest rate, but eventually it starts to tend downwards towards 1% again. If you look at the path for volatility, here again, these are these CV variables which change volatility through time. So volatility might be low, might be high at some points. And then eventually this is one possible path of the underlying asset. So the underlying asset drops first a little bit, then starts to increase, and so forth. Now, if you have one path, again, this gives you one realization of the underlying at the maturity date. Then you figure out what is the call price. You discount that back at these interest rates, and then you will have to take the average over all the simulated paths. So what does it look like? All these simulated paths. So this is for the underlying asset, 1000 paths simulated. So it's all 1000 paths combined, where this was just one of them. This gives you all these 1000 potential realizations of underlying assets. For each of them, you get one potential realization of the call price or the put price. And again, you discount them back and take the average. Notice in our simulation, we don't just do 1000 paths, but 10 million. So this picture is going to be even more busy.